Hello, everyone, and thank you for attending today's webinar, How Photovoltaic Systems Can Help Stabilize and Secure Utility Grids. I'm Kelly Pickerel, editor with Solar Power World, and before we begin, we wanted to let you know about a few things. There are a bunch of application widgets at the bottom of your screen. You can move these and resize these however you like. The slides are available to view at any time in the resource widget. And you can submit any questions related to today's webinar in the Q&A widget. We will try to answer these during the webcast. If we do not get to your question, our presenters may reach out to you afterwards. And finally, if you are watching this on demand, you can still use all the features I've gone over. So let's get started with today's webinar, How PV Systems Can Help Stabilize and Secure Utility Grids. Today's speaker is Dr. Daniel Faltermeier, Managing Director of Medio Control North America. Daniel has been a part of the Medio Control global corporate family since 2009, first as a manager of technical due diligence and then as the head of PV quality services. He obtained his doctorate in physics at the University of Stuttgart. And now, I'll turn it over to Daniel.
Thank you very much, Kelly, for this nice introduction, and welcome also from my side, everybody. We had a couple of people outside the U.S., so a special welcome to them as well. And let's get started for today's presentation, how photovoltaic systems can actually help to stabilize and secure utility grids. So what do we want to talk about today? Let's have a look at the agenda. First of all, clearly, I want to show you some company profile for these people who are maybe not so familiar with what Medio Control is doing. But after that, clearly, we want to dive deeper into the real topic, what actually the advantages of PV systems in the utility grid. So, as we all know, the landscape of PV has changed during the last years. And the load in the grid coming from renewable energies has reached a limit or has reached an amount which it's no way to not think about it as a utility company. So having that said, clearly both sides, the utility operators, utility companies, and of course the PV system owners, they have to think about what is going on right now and how to deal with each other. One way to help the utility is actually the power control function, which I will explain more in detail later, how this can help to stabilize the grid and take advantages from the photovoltaic system. But clearly, with the word control actually means that you can access the photovoltaic system or actually any renewable energy system from the outside, especially through the internet. High demands are coming up for more security. So you can imagine if you can access pretty much from any place in the world via the internet a critical infrastructure in the utility grid and shut that down, this will have a tremendous effect on the whole infrastructure. So clearly, with a higher amount of renewable energies in the PV or in the grid, also higher demands for security standards are coming up, and this is something we currently see with the NERC requirements, the CIP 5 standards in place. So when I look out the window here, I'm actually sitting in Chicago today. It's pretty cloudy and major thunderstorms are probably coming up in the next few minutes, but that clearly is not so good for the PV systems with high demand for good weather conditions. So when the sun is not shining, the PV side is not producing any energy. And if this happens very quick, so the clouds are moving over the side and covering the sun on a very short time scale, that is something the grid operator has to deal with to still be able to compensate the loss of the energy coming from the solar system. And how this could be predicted, actually I want to talk a bit more in the solar power forecast. But first, let's talk a bit about the company, Meteor Control. We are pretty much one of the oldest monitoring companies in the business. 40 years is a long term of development. And we, of course, are the largest monitoring company in the world with currently 12 plus gigawatt under monitoring control. So clearly, with that high amount of energy controlled with one single system, we have highly demand to make sure that all the security issues, etc., in the product is capable to handle that. So when we talk now about security, about work conditions, all that stuff later, we will do that from the view of a monitoring company, not from the view of a utility company. We have a very large data pool with performance data, and also besides the monitoring part of the business, we were involved in independent engineering service for now roughly an investment sum of $15 billion US. So what we do in this case, I will explain a bit later. Currently, we have about 170 employees worldwide with different locations in the world. So clearly, we are a German company. So the main headquarters of Meteor Control is in Augsburg in Germany, but with different subsidiaries. So one of these subsidiaries is actually the headquarters here for the U.S., covering the U.S. and the Canadian market here in Chicago. And also we have subsidiaries in Shanghai, in India, Spain, Italy, France, and pretty much all over the world. Recently, actually, we got a new subsidiary in the Japanese market. So, but looking on the history of Meteor Control, as I said, we are 40 years in the renewable energy sector, but the actual solar started in 1998 with the development of a monitoring platform based on the internet. And moving this timeline ahead, we invented the data logger as a tool, really building on site, gathering all the data, and providing this into a monitoring platform which can be accessed through the internet from all over the world. There are a couple of steps. I don't want to go through that in detail now, but you can see different milestones were coming up during the years. And for the newest milestone, I just want to mention that in 2015, we actually launched our new hardware generation, the Blue Lock, with different great advantages compared to the older one. You have live view on your data, higher resolution. You can have more than one inverter, for example, or more than one inverter manufacturer combined in the site. So you can use different inverter types. And as I said, we are actually the world's largest monitoring company in the world. So, but not only providing the monitoring solutions to our customers with the data logger monitoring platform, power control solutions, we also have options for full SCADA systems, which will be relevant when we talk about bigger sites with full NERC requirement, for example, later. But besides that, we are also offering technical quality insurance services started by the yield reports, technical due diligence, manufacturing audits, on all that stuff around the PV project. And also, and that's actually the third pillar, we are doing O&M service for our customers as well. So people can outsource the O&M service, operation and maintenance service to us, and we will take care about these assets in total. So right now we have a couple of NOx centers around the world. That is also an option for our customers. And having these two pillars beside them, monitoring business, of course, we know how to operate systems. We know what's necessary to build a good system up front, and taking all this knowledge into the monitoring system solution gives us the option to have a very precise or very taking into account any need from these two other pillars. So, but now coming actually to the topic I want to talk today, how utility grid infrastructure has actually changed during the last years. So thinking back a couple of years ago, the situation was pretty simple for the grid operator. That's the guy below there sitting in his control room, and his job is actually controlling controlling the whole grid. So, but the grid at that time, there are not so many players involved in that. You had one production unit, for example, a power plant, a nuclear power plant here in this case, and you had the actual grid, and of course some consumers at the end of the line. So what the grid operator had to do at this time, and which is still the main topic for them, of course, is to operate the grid. And what does it mean is you have to take care about the voltage stability, and you have to make sure that the power is where it's needed any time in the day or night, and pretty much operate the grid in a way that the whole system is stable. But when we look at the nowadays situation, there's still, of course, old-fashioned power production sites, but what has come in addition to that is a couple of new resources injecting power into the grid. And for the one hand side, this could be a very big utility size PV system, for example, which has maybe their own NOx center, their own operator. And on the other hand side, there are hundreds, thousands of households with very small systems, but all they are injecting into the same grid. And so new challenges for the grid operators arise from that. They have not to deal with one true production unit anymore, which they have easier access to. So now they have to talk to a bunch of producers in the grid. So clearly, most of you are familiar with how a PV system looks like, but here just want to show you one specific thing, and this is what I really want to talk about today. So when you look at the PV system, of course, you have the generators, you have the transformers, the grid, etc., a couple of devices gathering the irradiation, temperature, wind, or something like that. But you also have the inverter on site, and this inverter can do pretty good things. So we will come to that quite soon, or actually in the next slide, but the inverter has the ability to produce reactive power. And what does this mean? I will show you in that graph. So active power is pretty much what you can use to run a machine, right? This is the power you can consume here with a P. The formula for that is power is equal to voltage times current. But there are another part of the power. It's called the reactive power, and that is caused by inductive or capacitive loads in the grid. So, for example, the grid itself is acting as a capacitor, or machines in the grid are working like coils, or with the coils are producing inductive characteristics into the grid. And this reactive power is something you have to deal with when you do the dimensioning of the system. So the goal for the grid operator is actually to keep this reactive power as small as possible, because as you can see here on the right side in the triangle, the dimensioning for the inverters, for the grid, etc., that has to be for the apparent power. And apparent power consists of the active power and Q, the reactive power. So, but reactive power, it's not a real power. Yeah, you cannot use it. You cannot consume it. It's pretty much circulating in your grid back and forth. So the goal of the grid operator is to keep that as low as possible. And the good thing is, with the inverters on site, you have the ability to compensate the grid. So when higher load coming from inductive power or inductive reactive power is injected, you have to compensate it with capacitive power. So means you can just inject the opposite and get the Q down. And of course, by lowering the reactive power means F becomes smaller as well, and you don't have to go to higher dimensionings of the system. So what does this mean? Here's a graph. The voltage stability for the grid is very important. So you can imagine if you plug in your computer and you are not getting 110 volts on your power supply, you're getting, for example, 170, then the power supply will be damaged. So one of the main job for the grid operator is to keep the voltage in a certain limit. So the limit is actually 3%. This is what you can see here on the left side. But now having different methods to actually supply reactive power into the grid and compensating the grid. Reactive power changes the voltage level, or can stabilize the voltage level in certain ways. So when you do only active power control, so you shut down the active power in the grid, of course that means you are not able to put in that high loads to the grid. But if you find different other ways, like a fixed cosinus phi angle, cosinus phi is the phase difference coming to the reactive power, you see that you can inject a higher load by still keeping the voltage under these voltage limit. And moving forward to coming to a full power control, you see you can inject much higher loads. So with a normal function active power control, the load will be, for example, 3.5 kilowatt peak, while if you do full power control, you can inject 7.5 kilowatt, which is a lot of more. And that means there are great advantages for anybody in the field. So To summarize that, apparent power is relevant for utility grid dimensioning. So means lower reactive power, smaller dimensioning of grid is possible, means you don't have to pay so much for your power line, for your transformers, etc., for all the components in there. Utility grid operators can use the ability of the inverters to compensate the grid either in an inductive or conductive way. And there are also advantages, of course, for the owner of PV systems, especially if they are running facilities where they have motors, etc. So because if you are a company or a facility having a lot of reactive power produced from your motors, you pay for the compensation the grid operator does. So when you are able to compensate these reactive power more or less in-house, so that at the measurement point where the meter is, not that high amount of the reactive power is coming in or measured, then you don't have to pay as much. So with a PV system, as said, you can compensate your reactive power part, and that means if you have a system on the facility, you can compensate parts of the reactive power you have produced with your machines, so you don't have to pay that much. And inverters, and that's what I mean with that, can pretty much compensate the grid, losing, and that's very important, active power capacity. So this is something you get in addition. So you're not losing any active power. This is just injected in the grid and you get paid for it. But in addition to that, this reactive power can be injected to the grid. So it's an additional thing. But now what is power control? What does it actually mean? So I've taken here a picture from Germany from 2005 to 2010, and what it shows actually there is the beginning that the load into the grid is higher than the minimum load in 2009. So you're actually at that point where you have higher load in your grid as you can use, the requirement for power control as soon as a minimum load is reached. So that's why utility companies, especially here in the US, are starting more and more to have a look into the option and use PV systems to actually control and operate, or to help to control and operate their entire grid. So, but now have a look how SCADA system or how the power control system is actually working. So you have the grid operator. This is the blue line at the very bottom, and this grid operator, they have to talk somehow with the system. So, and usually they implement a YPN connection to a router on site. So, and this grid operator actually talks to a device called the PLC, power control unit, which could be, in this case, a separated device with a new generation of the blue lock. It's already included, is actually getting kind of values from the PLC. So grid operator talks to the PLC, and the PLC brings the specific values to the ECU, and then it's controlling from there through the switch the inverters, etc. But another component, which is very important in this case, is of course the grid analyzer. So we will talk about that in a few seconds. When you do the power control. So there's a demand from the grid operator for a specific value. Then you can either just implement that in the system, but you should get a feedback. So, and it's usually a round loop control. You get the feedback from the grid analyzer, which is usually set up at the injection point, in the interconnection point. So whatever you do on site or on the cable, so some of the sites have a very long cable between the actual PV system and the injection point. So you get the feedback from the injection point, and you have to adjust your inverters, your system, in a way that it still fulfills the requirement of the grid operator. When you have a look on the right side here on the slide, there are a couple of other things like a temperature sensor and radiation sensor. So, for example, the grid operator requires increment for the whole system. So you probably are not allowed to inject 100% anymore. You have to go to 70% because the grid operator demands that. So shutdown of the active power. You actually don't know what the possible power you could generate with your system would be anymore. So you need to find a way to analyze that or get a value what you actually could produce. And so that's done with a radiation sensor and with the system in the background. It tells you the difference of what you actually injected into the grid and what you could inject to the grid to know what the losses because of this shutdown or limitation actually was. So to stabilize the voltage, as I said, different remote control devices are needed on site. You should get different methods for reactive power control, and these methods are actually specification as a fixed set point or set by remote control, set point as. So, and that's different methods you actually can use. You can, the grid operator can have a demand for static cosinus C, their cosinus C characteristic curves related to the power. There could be reactive power, fixed reactive power value you measure at the grid grid injection point. And also you can do that reactive power independent on the actual voltage you have in the system. And of course it can be that the grid operator requires switches between different procedures. But at the end, all implementation at the grid connection point needs to be a closed loop control. So, but what are additional requirements for grid operators? First of all, they have the requirement for specific protocols they are talking. That could be different from grid operator to grid operator. So a very common way to do it is a DNP3 protocol here in the US, but also it could be an analog signal. It could be an RS485 or an Ethernet signal at all. So your device on site has to deal with these specific requirements from the grid operator, and they could be different from state to state, from location to grid operator to grid operator. So you need to have a device on site which can speak many of these, let's call it, languages. You have to the requirement for definition of reference points, different reactive power procedures, as I said, characteristic curves with 2 or 4 supporting points, or characteristic curves with histories. And that's the message you get back from the system to the grid operator, for example, is transmission of value of measured values like power, reactive power, or voltage. So the grid operator actually can also see and gets a feedback when they send a signal out that there is actually something happening on site. So, but as I said, now with the ability to really control sites, shutting down sites, that leads to higher demands for security standards. And the security standard coming up here in the US is actually the NERC CIP5 standard. So I've seen through a lot of conversations I had during the last time that this is kind of cloud. People from the solar industry are not so super aware, and they actually don't want to deal with all these security standards. But in fact, this is really nothing super complicated, right? And it's necessary to protect the grid from threats coming from outside. So nobody wants that the system, so the grid system, can be hacked from outside and the power going out. So what the NERC FERC or NERC CIP standards actually does, it's nothing more than protecting the infrastructure, right? You throw a border out around the NOx sensor, the different sites in the grid. So protecting the infrastructure is the main goal of that, and it's actually nothing else. So, but let's talk a bit about the names we are using here. So the NERC, North American Reliability Corporation, right? That's pretty much where all these, that's the company where the FERC give authority to implement all these standards. And the current critical infrastructure protection standard is the CIP5 standard, which was, I guess, now in place since April 1st. But what does it mean, right? Do I have to take care now about the CIP5 standards if I have a 10K system somewhere? So if I'm a household and I have my system on the roof, is that something I have to take care of all that stuff, or is it just for the grid operators who actually needs to implement these standards? And there are a couple of thresholds relevant for. So, for example, the NERC documents, they say for a system or portfolio of systems which is injecting into one interconnection point, 75 megawatt are relevant. So for that size, there are some CIP standards they will apply. But if you are moving on and you're aggregating more systems into a portfolio, and actually portfolio means you can control it from one single NOx sensor or one single system, and it's still in one interconnection point, then you have to fulfill full standards. So the NERC CIP standards are actually talking about three different things. They're talking about the bulk electric system, which is pretty much the generators, the transmission lines, everything, equipment in the usually 100 kV system or higher, so pretty much the grid. Then you have the critical assets, which is the facilities or the solar system, all things on the system, which can have an impact when something happens to the site and 50 minutes later, there is really a change you can see, or is infecting the grid. And the critical cyber assets, actually, these are the parts you can program directly on site. So any computer, any hardware device can be reached from outside and can be programmed. This is the critical cyber asset. That's what needs to be secured. So SIP standards, actually, there are a lot of chapters, but at the end, it's a normal thing, right? There is nothing special. It's for any computer center in the world, these same rules probably would apply. And it's talking about security management control, electronic security permits, system security management. But what does this actually mean, right? It goes down to the fact you have to think about your password. You don't write the password on your keyboard or something like that. So it's not super high fancy stuff they're talking here. It's pretty much basic regulations you have to fulfill to make sure that your cyber assets are secured. Also, that goes a bit further, is incident reporting and response planning. So what if someone hacks? You should have a plan how to act in this case. So running away or screaming is probably not the right scenario or the right thing. So, but it's not talking about specific actions you have to take. So it's more talking about be prepared. Think about it. What happens if something was hacked, and how can I recover all these infrastructure, information protection, etc. And of course, the physical security. So when you have a NOC center, you need to make sure that not everybody is entering this NOC center. Only trained people should have access. Only authorized people. You have to document it. You have to close the door, and there needs to be specific keys to come in, and these entrance has to be documented as well. So it's something you would have probably for any other NOC center, for any other computer center in the world. And of course, you should train your personnel. People should know if they're working there what to do. So it's not super complicated. It's just basic things both sides have to think about. So chapter 2 actually talks about the classification of the system. So what is now relevant for me as an owner of the PV system or of the owner of a NOC center? So there are 3 levels. This is the high impact level, which is relevant most of the time for huge utility control centers, right? For utility operators, etc. They have to fulfill that. Medium impact could be for large portfolios, control centers. But most of the time, PV systems are in the range of low impact. So, and that means you have to implement just the cybersecurity awareness. So think about it: physical security, electronic access control, and incident response. That's the point we talked about. So at the end, the NERC SIP standard is not so complicated. It's more talking about how to protect the NOC center and how to protect the system being you're from outside hacking, for example. And for us as Meteor Control, these 2 red lines, these are usually in a response for the actual operator or the owner of the site. What we as a Meteor Control monitoring provider have to make sure that our unit, the grid operator or the site operator, is talking to fulfill seamless all these requirements from the NERC standard. So, but now coming to the last topic, the solar power forecast. We talked about if people are hacking the system and they're able to shut down specific sites or larger portfolios, that will have an impact on the grid itself, because it can have a cascading effect if some load is dropping instantly out, and it's not possible maybe to compensate that anymore. But same thing could happen if clouds or different weather conditions are leading to the point that the system is not producing energy anymore. So, for example, if a thunderstorm is moving very fast over the solar system and you're not aware as a grid operator with a very large site dropping instantly out of production, you are in the risk not being able to compensate the grid anymore. So a tool to actually know that upfront is the solar power forecast, which gives you as a grid operator a view what will happen in the next minutes, to be prepared actually what reaction has to be done in the short future. So, but what is power forecast? We all know the radiation forecast. This is pretty much something you get out of satellite images or the NYP, so the normal weather forecast, and of course irradiation sensors on site. So that is just giving you the information how much sunlight will be coming on your site, or how much irradiation will be on your models, but it doesn't tell you as a grid operator what the load actually in the grid will be. So in combination to that, there is also the need for really transferring irradiation to the actual output of your site. And for that, of course, you have to know what the PV system or the portfolio is look like. So how much energy will be produced from this irradiation. And so the combination of those two things actually lead to the point that you are able to really get the full the power predicted, and not only the irradiation. So, but how do you do that? So we already know the normal, the numerical weather prediction. That's the weather forecast you see on TV every day. It shows you on a time scale what the weather will be in the next few days or whatever. But it's on a short time scale. It's actually not very precise. So you need another tool giving you the information what will come up in the next few minutes. So, for example, in this case, you could use satellite pictures or cloud motion models. That's how it actually looks like. What you do in this case, you have a picture from your satellite for the clouds, and then you go back 15 minutes and look how it looked like at that point, and then you do a kind of motion vector between these 2 points and a prediction what will happen in the next 15 minutes. So giving you a picture what or where the clouds are moving and how fast they are actually moving. So these two methods actually are available. So you have the cloud motion model and the normal weather forecast, and both of them are somehow okay to predict the real world. So what you see here in this picture, the blue curve is actually the prediction from the weather forecast, while the red curve is the real value. And you see the blue curve is still below the red curve, so it's not obviously not describing the reality perfectly. And also the cloud motion model is not providing the reality in a good way. So what you have to do is actually use both. Put everything together using the advantages from the crowd motion from satellite, which is a precise forecast for the next hour, the numerical weather forecast, precise forecast for long-term horizon, and of course the power prediction from monitoring. Gives you the actual PV power production. So, and having a look and how precise these methods actually are. So the root mean square error for method number 1 with this normal weather forecast is here 41 watt a square meter, and you see the if you do the cloud motion, it's 34. But if you combine both methods, you can come down to 25 watt a square meter. Root mean square error, which means you gain a precision of 39% roughly compared to the normal weather report, or in combination 2.6 better to the normal prediction. And that means you can have a very high reduction of the extreme values. So your measurement of your forecast is much more precise at the end. So let me summarize today's talk. Inverters can help to compensate the utility grid, so it's actually a very nice tool to help grid operators compensate grid and not to spend so much money for grid expansion. With higher solar or renewable energy systems in the grid, there is a demand for power control. So at one point, I guess it will be also mandatory that your system can manage or can handle the power control function, that grid operators can manage it or use it. Of course, by having the access to the site and really physically changing something on site with a computer anywhere in the world, new security standards are also necessary, which we will see with BIP 5 and all these standards coming up right now. And for a very variable asset in your grid with a high fluctuation because of weather conditions, it's super important to know what's going on. And weather forecast, power forecast actually can help grid operators to have a way to act on possible scenarios coming up. And for that, of course, reliable forecasts are required. So that's actually all I want to talk about today. Thank you very much.
All right, thank you. We're now going to open up the floor to some questions. Remember, you can continue to submit questions at any time with your Q&A widget at the bottom of your screen. So here's our first question. Can reactive power also be provided during the night?
Yep. The simple answer on that is yes. As I said up front, it can be produced in addition to the active power, and even if there is no active power provided into the grid, with the way this triangle works, there is still the option to have a amount of reactive power produced to the grid. Means even during night, where the system is clearly not producing any active power, reactive power can be injected into the grid and be used to compensate the grid, even if there's no production from the inverter.
Okay. Does the owner of the solar system get money for providing reactive power?
I guess not yet, but that is probably something I would think will come up why it's soon. So it's actually the same as you pay money to get compensation from the grid if you have a motor or a facility injecting usually inductive loads into the grid, and you pay for that. So why you should not get money back if you are producing reactive power, the grid operator on the other hand side can use to compensate. So I would think this is something for the future. I'm not aware that any country in the world is already paying or have a concept for paying reactive power. Maybe you can let me know if I'm wrong with that, but I would assume having this nice tool that you probably will end up in a couple of years that you get paid for that in addition to the active power you produce.
Can Meteo Control provide your forecasting anywhere in the United States?
Yes. So that's highly related to the access to these cloud motion pictures, to satellite pictures. So we have access to all these. So the history actually of Meteo Control is strongly related with, and that's why the name says Meteo Control, to weather forecast and weather prognosis at all. So yes, we have access to our own database, satellite data, or we can cooperate with companies. That's what we do here in the U.S. to get very precise satellite data, and that is something we use for the prediction. So the prediction or the forecast can be done everywhere in the U.S. right now. Yeah.
Is the forecasting available outside of the United States?
Oh, yeah, absolutely. So clearly it comes from Europe. Europe is something covered completely. There are probably some areas in the world we don't have or we haven't done it, but clearly where satellite data is available, you also can do the power forecast. So the only thing is probably we have to buy these satellite data from other companies where we don't have our own. So, but that's the only limiting factor. In fact, you can do it wherever you want. You just need the satellite data. But I would say 90% of the world is already covered.
All right, perfect. Well, that is all the time we have for questions today. If you have additional questions or we didn't get to yours, feel free to contact our presenter on your own. And again, this webinar will be shared with all registrants, so you can view it again at your convenience. I'd like to thank Daniel again for being here and Meteo Control for sponsoring today's webinar. And thank you to everyone in our audience for participating. I hope you enjoyed our presentation, and we invite you to join us for more Solar Power World webinars. Thanks, everyone.
Thank you very much.